I'm going to talk about the growing expectations of engineering maintenance over the years. And there's three types of generations, which are the first generation, the second and the third generation. The first generation, which was the period up to the 1950s, in this generation industry wasn't very highly mechanized, so the downtime on each machinery wasn't a big issue. So people used to implement breakdown maintenance, where you fix something when it's broken down, basically. Second generation, and the example for the first generation is actually a hammer, which is a simple mechanism. And on the second generation, this was the period during the 1960s to 1970s. In this period, the industry was dependent on several complex machines, which were lasting longer equipment life, and there was more high plant availability at lower cost. And the example for that in this generation is the drill press, which you can see right here. In the third generation, this was the period from the 80s to now. In this generation, there's more new expectations of engineering maintenance, and there's more new tools which are being designed, sophisticated. One of the examples of this generation is the plant which we have down the hallway. And there's more greater safety mechanisms and a better product quality.
There are four main different types of maintenance. They are breakdown maintenance, preventive maintenance, predictive maintenance, and design out maintenance. An example of breakdown maintenance is where an object breaks down without prior knowledge of it. An example of that is these augers on the Zamboni getting clogged. When they get clogged, the machine is redundant, they have to be cleared out, and then before the machine can get put back into service. An example of preventive maintenance, once again on the Zamboni, is simple checks like oil changes, the hydraulic fluid and engine oils, basic servicing, emission controls to make sure that the machine stays at the basic operating standard. Another type of maintenance is predictive maintenance. Although the surface device doesn't seem like a machine, it moves and acts the same way. We predict the maintenance by drilling holes in the ice as such and measuring the depth of them with a vernier caliper. After we've measured the depth of the ice in about 60 places, we can mark them on a schematic of the ice and detect what areas are low and high. From here we can detect what areas are getting the most wear, and from there we can add water to those parts at night when it's needed. Another type of maintenance is design and out maintenance. Design and out maintenance is redesigning a part or making it redundant due to having to maintain it too often. The prime example is this blade that's mounted to shave the ice. This blade is currently made out of mild steel and has to get sharpened once a week. If it was made out of steel such as stainless 316, it may last a lot longer and further time between sharpenings. Sometimes this is not feasible or worth doing though, because the cost of sharpening stainless blade might outweigh the benefits of keeping this a mild steel. When it comes to design out maintenance, there's several factors which must be considered. The first one is technically feasible. When saying this, I mean, is it actually possible to do this, or are you asking yourself to do a possible task? The second thing is it worth doing? For instance, this plant room where these compressors cost hundreds of thousands of dollars, is it worth replacing them when the payback period on a compressor may be years and years beyond its useful working life? These are two questions you have to ask yourself when you're considering design out maintenance. Many people associate maintenance with basic maintenance activities. These are the most common activities usually performed to maintain the quality of a machine. This machine here is Zamboni 445, which we're going to be demonstrating a couple of maintenance activities on today. Activities on this machine can consist of things like a normal car, like an oil change and engine service. As this is a hydraulic machine, there's also a lot of hydraulic servicing to do on it and water flushing. The two most common activities performed on this machine are gas bottle changes and a blade change, which I'm going to demonstrate how to do now.
There are two types of failures in a system. There is degradation and catastrophic failures. Catastrophic is a sudden and more dangerous failure. For example, this here is an ice edger, and it is used to shave ice off the edges. And it spins at 5,000 RPM, and you can see here it's fractured here, and that's a very dangerous mode of failure. And yeah, there's also degradation failure, which is gradual over time, and it's a predictable mode, unlike catastrophic, which is usually unpredictable. For example, these blades here on the edger, they dull over time and need to be replaced, and it's generally happens in the same period, so it's predictable. These two modes can be a result of three things. First being machine design, which is material choice from the designer or lack of redundancy in parts. So there's so many parts that it can fail easier. The second is quality of construction, which can be poorly sourced materials during manufacture, or poor construction, as in construction defects, which cause the part to fail. The third is operation, which can be a result of poor maintenance strategy or inappropriate use of the product, which can develop stresses which wasn't designed for, or poor or different environmental conditions than it was designed for, and that's a result of use from the consumer.
Failure analysis is a big part of engineering maintenance. An example of this is early life failure. For example, this drill bit has gone through excessive torsional forces. This can be due to poor design, poor quality of manufacturing, defective or inadequate componentry, incorrect installation or commissioning, incorrect operation or misuse, unnecessary routine maintenance, or bad workmanship. Another useful topic of failure analysis is wear-out failure. This failure can occur through a variety of different reasons. For example, wear, corrosion, fatigue, and looseness. An example of this is this flat disc sander, which has a variety of flat sandpaper flaps. This is used to polish metals, and over time this loses its abrasiveness. Another topic of failure analysis is useful life. Useful life occurs approximately uniformly over the period of the product's life. For example, this forklift, it served its useful life and is now breaking down for a number of causes.
Okay, in this plant system we have 4 compressors which are in parallel network, which means if one fails, we turn on the other one.
These compressors, which are in parallel, are linked in series to the condenser, which is outside, which is linked in series to the Freon pump, which is linked in series to the ring. The ring works as an evaporator, which completes the refrigeration system. This whole system is in series, as if one of the components fail, then the whole system fails.
Because all of these compressors are linked in parallel with all the other components which are linked in series, this makes this plant room combination system.